the props. Design of props is based on three things. One is what is called, you probably are familiar with serviceability limits. That means how much, if this fly-through prop is going to sag, because let us say this going from one end to the other end, this particular case is about 35 meters. Imagine you got a tube that is held at the 2 points, 35 meters long. It's going to deflect, yeah, by its own weight, self-weight. The self-weight deflection of that prop is going to pull the walls in, because if you got a basement of, let us say 40 meters by 40 meters, if you say I want to put a fly-through prop like this is the plan. So that prop, which is supported by a capping beam there, capping beam there, is like a simply support beam. Under the self-weight itself, it will sag, right? Under the self-weight. So what happens to that deflection? When that prop deflects, it will pull the walls in. So you got to think, what happens to the serviceability state during construction of that prop? What is the self-weight deflection? That prop is roughly about a ton per meter. So 40 tons beam is standing. When you start, although you install it while the ground is here, you're going to dig underneath it. Once you dig, it starts to deflect by its own weight. Once it starts to deflect by its own weight, it will pull the walls in. So serviceability limit state is about what is the deflection of that prop. If a fly-through prop is very large, so what we do is we jack it up. So we hold it up. So when we install, we hold it, we put it like that. When we release, when we dig the ground, it comes flat. So there are two ways of controlling if the deflection is too large. And to realize the forces in this, it takes a bit of time, we know that. If it is gravel, you can see, as soon as you dig behind the wall, it will push. Yes? If it is gravel, the forces are acting very quickly. If it is clay, it will take a bit of time to build up the forces at the back of the wall. So again, you have to think in terms of what is the development of the force with respect to your sequence of the construction. So once the force is developed, then we also look at what is the ultimate limit state scenario. So that is based on the strength of the material, using material safety factors and so on, load factors and material factors. We work out what is the force, what is the utilization in these props, how much force is developed in the ultimate limit state. So that gives you a safety in terms of developing the forces. So remember, the force in this prop is not developed on day one. It developed while you are digging slowly to the formation level. When you put the force is only self-weight, when you start excavating, then the force starts to develop. So once the force starts to develop, it's going to compress this one. Is a strut, so it's a compression member. You got to think of buckling and then making sure in these props you have allowable stresses. The stress, there is a margin of safety in terms of the forces. So why they are circular props, you think? Yeah. 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 What else? What are the other reasons why it is circular props? Why not a big, massive concrete beam or something? Yep.
Same way.
Yeah. Yes. Good point. Yeah. Any other reason? In terms of the fabrication, in terms of the splices, circular sections will give us flexibility to bring the flanges to bolt it. So it's simple, it's safe to bolt it on site. So imagine this is actually, as I said, is about 40 meters. You can see the splice there, the splice there. So these splices are easy to install. And you can see clearly what, the alignment and all is easy with the circular props. Also, why do we use sections that are not proprietary? It depends on what is the program. So you can go to the market and buy or rent these props, but those props will have limited load. Yeah. So you can say, oh, I'll buy it like off the shelf. I can take a prop which is nicely bolted to my capping beam or whatever vailer. If you got a steel vailer, you can see here there is a capping beam here, or you could have a steel vailer if it is a steel beam. So you can bring a proprietary systems to bolt it and then use it. But you will find if you do a cost analysis, the proprietary systems, in terms of the rent that you pay for those things, is that it's very high. You might as well go for some props that you can fabricate on site and reuse it. So what we normally do, because we are contractors, we reuse the props again and again. So that's again sustainability. So we don't just throw these things. They will go back onto the yard, and whenever there is another scheme, we reuse the props, we cut them and modify to suit. So that's the beauty of these props, when we make them specifically suited for our jobs. So proprietary props also have got limited capacity. In this one, the force we're talking about is about 2,000 tons. It's a massive force. Yeah. What is the disadvantage in the steel when you are digging blue sky? What happens in summer? What happens in summer? Exactly. So it gets really hot, yeah? So in this particular scenario, we were working in a blue sky option next to King's Cross Station. This prop gets exposed to, in summer, out there, something like 35 to 40 degrees. Yeah? So if you put a simple equation of a prop, so imagine this is delta T is equal to 40 degrees. So that prop of length 40 meters, so your delta is equal to alpha T times length. Yeah? That is your deformation or elongation of the prop, isn't it? So alpha is the thermal coefficient of expansion for steel. T is the temperature. So what you got there is a prop of that circular dimension of about a 1.2 meter diameter prop, and for steel it is 12 into 10 to the power of minus 6. We talk about temperature roughly 40 degrees centigrade. L is being 40 meters. It's a huge force. Yeah? So again you got to think, when the excavation is going in summer, the force is huge because of the temperature. That's being restrained by this huge capping beam. So it's going to develop extra force. Yeah? Remember, it's not nice freely to expand. If you let it expand, it's fine. But you can't let it expand because it is held by those big, thick corbels at the end. So you are developing a huge force in the prop in summer. Again, it's something that we have to think. One of the things that you probably remember, if you go back to you see what we have done there? You put insulation, because that force is massive and the prop is going to buckle. So what we did was we put a lagging, basically a lagging outside to maintain the temperature so it doesn't see 40 degrees temperature. This is again in London. Go to the construction sequence, almost 9 months. We will see hot summer periods. We want to control the forces in those things. We lag those props because they are the longest props on site. Obviously, the longer the length, huge force development. But you're short, doesn't matter because it's very long. We talk about this is one of the largest props used in London. It's a 50-meter long prop. Yeah. So you have to think in terms of when we talk about ultimate limit state, what is the temperature force added onto the prop force? And that component, do not underestimate, it's very huge. If you let it go, it's fine. If you can't let it go, it's all locked in here, the force will go up. So the other one is about accidental limit state. What is this accidental limit state? Why should I worry about accidental limit state? Anybody heard about accidental limit state? Yeah?
When you, like, say, if you're holding back water, you have maybe a ship crash into your seat.
I agree.
And
Yeah.
you can have accidental loads.
Okay. So what is the scenario you can think of here that can create an accident?
Yeah.
Collisions, isn't it? So Remember one of the sites I showed you, we have a big tower crane lifting 5 tons of steel. Yeah? Or maybe a cladding or a piece of brick, whatever it is, 1 or 2 tons. So accidentally, if it gets dropped on this, yeah, you got to address what is the force in this and what is the redundancy in the system. So imagine again, if you got a 50-meter long prop, yeah, and if you drop, unfortunately 5 tons, which is 50 kilonewtons, you can see the bending moment dramatically goes up, yeah, because the prop is long. And accidental impact, again you have to think of dynamic impact factor, which is roughly about 2. So static load is 50 kilonewtons, but dynamic load is maybe 2 times that, maybe 2.5 times. Whatever is the dynamic impact factor, that is only static load. So times the dynamic load factor is your force impact applied on top of the prop. In that scenario, you must ensure that there is enough redundancy in the system, the prop is not going to fail. Because if that prop fails, the wall is going to come in. Once the wall comes in, there's no going back. Yeah? So, this is another thing that we have to demonstrate. For the props that you are putting, what is the accidental limit state scenario? If one prop fails, you have to imagine there is a redundancy in the system. And there have been major incidents in temporary works where one prop failed is like a pack of cards. Everything collapsed. And there is no going back. Because the walls moved in, the damage is already done. The whole thing came in. Yeah. So it is important that you address the accidental limit state in these scenarios. It could be a drop of a concrete bucket, it could be a drop of a brick tile, it could be a drop of a reinforcement block on those walls. You must ensure that the redundancy in the system is not compromised and there is enough resilience in the system. I talked about monitoring. So, in order to ensure that our predictions, because you remember in soil mechanics, the predictions, you based it on certain number of boreholes, certain number of tests, certain number of coaxial tests, certain number of rain shear tests, certain number of all the tests that you do in classifying the soil, calculating what the properties are, engineering parameters are. But you get always a range, as I was saying before. You get what is called a lower bound solution, you get what is called most probable solution, you also got a worst credible scenario, which can never happen. So those three will give you a range of values. So it is important that we monitor how the structure is behaving as you are digging, as you are excavating, as you are building the structure. So what normally we do is we put a 3D surveying. If we got a big facade here, we use the big monitoring of the facade, how the facade is actually moving in. This is a plan view of that excavation I showed you earlier. There's a 100-meter long facade here, and we put inclinometers in the tube. So the tube, when you're actually driving, even if it is a secant pile, there's a hole of 150 millimeter diameter. You drop a tube in there, and then within that one you monitor by using a small torpedo. It gives you a measurement how the wall is doing. So we use what is called inclinometers at various regular intervals. So when you're doing the sheet pile, at the back of the sheet pile, you weld the tube, and then you drive it with it. So if you weld a tube there, and in the tube you drop a torpedo, it will measure how the wall is moving as we go down. So that inclinometers is used, and then we use the load cells on the props. So when you're actually installing the braking prop, as I was saying before, you can put a load cell on both ends or one end, so you can measure what is the load of the prop. And then if you got services here, obviously in this particular case, it's surrounded by roads. So we got the Thames water main, we got gas main here. So on the pavements, on the roads, we put the studs to see the leveling studs, see how that settlements are happening on the ground, just outside our boundary. And this shows clearly, if you take a typical inclinometer, this is monitor 17, you can see, because this is actually a raking prop, you can see how the wall is moving at various stages of construction. So this shows how the wall is moved as we started to excavate, and you can see the point of zero or contraflexure is well below the formation level. This is the formation level. So the wall is not moving here, more or less you can argue it is roughly fixed at this point, and then it starts to move, okay? Which is what you expect. And you can see a bit of rotation there, and that is what we talked about the other day. How do we relate the volume loss or the movement or the change in strains into the settlement contours of the ground. So if that moves, ground here also differs like that. Yeah. So you can relate that to the ground settlements in Bhagram. This is another inclinometer reading. You can see so you can see here, even if this is, we think it is fixed, it's moved a couple of millimeters here. It's almost at this point something like 5 millimeters. So that's happening in the ground where you're not dug. Yeah, we've dug only here, but the movements are still happening. 4 or 5 millimeters. So what that means is, if this number is significant, remember that you need to reflect that back into the ground. If this is moving below that, that means your influence area outside the footprint of the building is also changing. So what I mean by that, if you don't have enough fixity of the wall, so again imagine this is a 40 meter by 40 meter construction. That's the plan. Yeah. And if you take a slice through there, what we said was, if this is the formation, if the wall is moving below the formation, it means the ground settlements are influenced by the same dimension on this side. That makes sense? Because the volume loss has to be the same. If the fixity point is here, the influence of the ground outside the perimeter of the building is limited to what you are digging. If you put a very shallow one, you don't know, but this is moving. This point is moving. If that point moves 10 millimeters, that means, let us say if this is 10 meters, this is 5, that means 15 meters at the back of the side, the ground is actually start to move like that. So that is actually 15 meters. Who would think that you are digging 10 meters and 15 meters down there? He or they can see what is moving and they can put a claim on it. Yeah? So the contractor have to address these issues. What is the movement of the toe of the wall? We think the toe is nearly fixed. That's fine. In some cases, the wall, the clay is so flexible, sometimes the stiffness of the clay varies dramatically, depending on the strain levels. If the strain levels are large, it starts to move, so the toe movements are also related to your ground movements. You've got to be careful of what is the influence zone outside the boundary of your site. So you have to do the risk assessment of all those. So in plan, so what you think is that we are digging, let us say you are digging 5 meters, so you think that the influence zone is only 5 meters here. So you do the assessment, risk assessment of all the structures and buildings and everything within that one. But if the toe keeps moving, your influence zone, yeah, changes. So you got to think, you have to bring in more buildings within the properties, whatever is there, you got to do risk assessment, submit those risk assessment to all the third party owners, whoever owns those buildings, and ensure that whatever operations you are doing is not damaging these buildings. Yep. So it's very important we monitor this as we dig and keep what is called a sort of a, controls. How do we actually control this? So one thing is fine that we keep monitoring, but what do we do after we got the data? So this is one example where we measured the loads and we compared, because we put the jack on the raking floor. So the jack actually picks up the force as we go down, as we dig down. So it actually tells you what we predicted, actual load versus design load. So in various soil conditions, we're getting roughly about 80%. And then in terms of the predicted and movements, we do various types of analysis. What is a wall-up, which is a beam and elastic foundation approach. And we use a non-linear low strain 3D modulus. We get some sort of better control, better measurements, and what we measured is that. So you can see wall-up gives you generally a better estimate, a safe estimate, a conservative estimate. And then if you go for a non-linear, because the clay is highly non-linear depending on the plasticity. So depending on the strain levels in the clay. So that particular one, if you bring into the model, this is a detailed finite element analysis, you can see you will improve the figures in terms of your predictions. What we actually measure is That's a good name. So again, the variation of the stiffness is very high, certain soils, and we need to be aware of that. We talked about props, and sometimes it may not be possible to put the props, either fly-through or raking props. So we come up with something called ground anchors. Yeah. So the ground, you can see drop the ground, we push a big hole in there, put a distressing rod, grout at the end, and then close it there. So we basically stress it. So in section, how it will look is, so we can't put the props into the site has to be free. So if you are digging to that level, let us say 10 meters. So that's the sheet pile we have done. So we drop the ground about a couple of meters and we put it in there. So we put a ground anchor. And then grout it here. So that is all held in nice stiff soil. Obviously you can't put it in loose soils. All that, whatever the force that is coming here has to be by bonding by concrete into the fish. So you lock it here, and then that way this space is free. So why I can't use ground anchors everywhere else then? Yeah. Loads, yeah, that's one of the reasons. Will you allow ground anchors to go behind your, below your building if I am digging next door? That's the reason. So we can't put ground anchors next door because that area where you got buildings or a highway or anything here, nobody will allow unless you own the site. Nobody will allow. Although you are going very low, very deep and so on, they won't allow you to dig under their building and put the ground anchor. What is the other disadvantage of the ground anchor? Let us say the client owns the site. Why I cannot put ground anchor? What is the disadvantage of this? As you said, the loads are very large, so you need lots of anchors. So you can see the spacing of these anchors is hardly 3 pans, it's very closely spaced. Yeah, the spacing, this is about 500. You can see these anchors are spaced about 2.5 meters, very closely spaced. But the anchors take limited load, and that limited load is based on the bond at the end. If that material is not good, it will come off. So it is limited by what is carried by the bond at the end of this. That's the force is holding. And you're not sure how much grout has gone, how much it is holding, unless you test it, right? So you've got to test it and so on. What is the other disadvantage with this? Suppose there is a, so if there is a break, somebody accidentally digging behind, although it is your side, somebody accidentally digging, if you put very close to it, somebody accidentally hitting it, it breaks, and then you have an issue. So although you own the property, again you got to address what is the scenario in terms of accident.
Are they temporary, permanent?
In this case, they are mostly temporary, because if you are using as a permanent condition, there is a clause that you must prove that they are not damaged by any means. So if you are using for, you have to do a risk assessment. If you are using, all right, I'm using temporary purpose, my ground anchor, you have to ensure 60 years it is going to stay in the ground. Yeah. Somebody coming next door, he will not or they will not know that there are ground anchors. They will simply start digging. Yeah. So that risk is there. So you got to ensure, if you are using them for permanent condition, how do you ensure the neighbor will not come and build another basement here? Yeah. At some stage in the life. Remember, the building life is 60 years, 120 years. So accidental condition of the ground anchors, even during temporary condition, we have to demonstrate that we are not losing the stability of this wall. Remember, we have already exposed the wall here. If that ground anchor is broken, this wall is going to come in. Once it comes in, there is nothing that can stop. Yeah. So you got to think, again, you can see the strand that is being jacked here, is a pre-stress wire that you put in, you pour the concrete and so you stretch it and you lock it. Then you lock it on the template here. So the force is held there. So you need to ensure that force is constantly held there. If you lose that force, the wall is going to move. Yeah. So that's another ground anchor system. We do use sometimes, if we know exactly what we are operating on, we use in the temporary conditions. We also ensure that we are not putting a demarcation zone. No machine can go and damage these things. Yeah. So you got to put what is called exclusion zones where the ground anchors are. Sometimes you will see most of the ground anchors are used in big retaining walls and marine structures. So sometimes you get a footprint of those things, what is being used. Sometimes we use them multi-level. So sometimes you may go here, put another ground anchor here, very deep one. You go to the next one, put a very deep one. So they are very long. So you got to have a multi-stage. We are doing this in one of the jobs where we are putting 5 levels of ground anchors. 5 levels of ground anchors to hold the wall. So they are closely spaced, very closely spaced, and making them also very long as they go in, and ensuring that none of these gets damaged while we are excavating here. So ground anchors is another way of holding it instead of prop. If you can use the ground anchors, the thing is about limited capacity, damage criteria, and what soils it is going to get the develop the bond that gives you the force to hold things. So this is another one where you can see the prop. This is the longest prop we talked about. It's a 50-meter long prop. This is diagonal prop, so that's the capping beam. You can look at the offset here. So we were measuring wall deflections, we were measuring prop loads, we were measuring temperatures, we were also measuring all adjacent buildings, and the roads, and also the heave at the formation. How much, what is a heave? Why does the ground heave?
Use the stress release and then ground.
Yeah, absolutely right. Yeah. So what happens is if you again go back to the scenario of deep basements, not very shallow basements, but if you let us say you're that's the formation level, this is the secant wall, that's the ground level, that's your original ground level. Now what have we done to the soil there? So sigma V, before you start digging, that is, this is 20 meters. So gamma H is equal to 20 times 20, that is assume total pressure, 400 kilopascal. That's the vertical pressure on this, yeah, on the soil particle. By digging, what have you done? You made sigma V is equal to 0. So what happens to the bulk modulus of that? So the ground is going to heave. If that ground is going to heave, so this also going to come up. Yes? So behind the wall, remember, this is the center of the ground, center of the excavation. That's the maximum in the center. So if you got a plan view of again 40 meter by 40 meters, the settlement the heave contours will go like that, right? Because that's the maximum. Yeah? Then it goes to the end, it gets less, and then it changes the curvature. And because of that, the ground also heaves. So if you got a pipe there, that also comes up. So again, you have to think, what is the heave when you are doing a bottom-up excavation? Because by the time you got down to this level, you dug 20 meters, within 6 months, you are there. So on that soil element, you have made sigma V, vertical component of the soil pressure, to 0, because you've excavated all the soil. Suddenly, you can't build the whole building, 20 story, 30 story, in one day. You just left it open. So you saw that ground where we opened everything, the ground is heaved. So we measured the ground heave by putting what is called extensometers in the ground, in the holes. So we do that from day one. So we put it installed there, and we measure how much the ground is moving. And obviously in gravels and coarse grained soils, heave is very instant, immediate, but in clay, it happens very slowly. So most of the time you will see during the construction period, 40–50% of this stuff happens, but in the long term, there is a lot of residual heave. Yeah? So when you take this 400 kilopascal pressure out, then we are building bottom up. So you are slowly building the pressure here onto this one. So you built one story, now you already excavated it, the ground heave. Now you started building floor 2, floor 3, B1, B2, B3, B4. You're slowly building the pressure. If you come to this 400, then it is okay. But if you have already put only 300 in the back end there, by building whatever the multi-story building you are building, the applied load when the new building has come, let us say it is only, you put only 300. So the residual is still heaving. So you got to think in terms of the long-term movements, what is the, because what you have taken, you have not put it back. Yeah? So you got to think what is the net pressure is going to push my slab. So what people will do is that pressure, whatever the base slab you have applied here, is going to push that base slab. Yeah,
When your piles work in tension.
absolutely right. Yes. Yeah, absolutely right. Yes, the piles will start working in tension. That is why it's important to see whether the load balancing is being done by the new building. Yes, piles will absolutely, they will go in tension. That's why you have to ensure the cage is there, and your slab is also subject to pressure. So how do I relieve that? How do I relieve that pressure? If the pressure is, residual pressure is very high, my slab is going to be 1 meter or 2 meter thick, yeah? What do I do? How do I release? How do I reduce my 2 meter thick? So if let us say, if the difference is 100 kilopascals, yeah, let us say, for argument's sake, that means I have to put almost 4 meter thick slab to hold it to 100, to just 0. Yeah, 4 meter thick slab is equal to 100 kilopascals of pressure. So I need a 4 meter thick slab to balance the load so that my heave pressures are encountered by the dead wall. Yeah, you understand what I'm saying? So is that practical to put 4 meter thick? Is as thick as this? Yeah. So how do I deal with that? What do I do to reduce those things? Anybody think? Water? Yeah, where will you put the water? In the basement, the swimming pool. You can put a counterweight, but again you're occupying space, right? You can't put a counterweight. So if you say I put some counterweights here to hold it down, because the heave is pushing the slab out. Yeah? Yeah? Any ideas? No? Okay. So if the heave pressures are very large, that is a slab. So we talked about tension piles here because it is subjected to upward pressure, which is the net long-term residual heave acting. That's your ground level, that's the formation level. And we put a reasonable thickness. But the slab is subjected to this pressure between the piles which are actually acting in tension. So to reduce this one, what we do, yeah?
So that like a gap between the ground and the slab and stuff.
Yeah. So what is that cap? So what we do here, we put a compressible material. It's a filler. So basically the heave squashes that board and doesn't apply the pressure on this one. So this is basically a compressible fill. So we estimate how much it is going to compress in the long term. We lay the board and then we pour concrete. Number one. Number two, you can leave a gap. Physically it is very difficult to leave a gap because what happens is, if I am leaving a gap, how do I cast that concrete? I have to put the shutter, right? To pour that concrete. So I can't pull out the shutter. Yeah? So what we do is we lay a very soft board, which is about that thick. Generally it's about 100 millimeters, 150 millimeters. So we lay that on the ground and then pour concrete on top of it. When the heave pressure comes, it squashes, it doesn't apply or it doesn't transfer the load onto this, but the piles are still subject to tension. So that's another thing that we control the heave in those. So it's important when you go into a deep basement, you measure what the heave is and predict based on what is happening in the short term. Because we dig about 16 meters here, maximum heave is happening here, and then edges it will be controlled. Okay? So those are, so this particular one again we put the inclinometers. You can see the inclinometers. We got so you can see the readings here, and that's one level prop. You can see the final shape of the wall is, and below the ground, so almost 20 meters below the ground, the wall is still moving. So if you reverse this one, so the influence zone of this structure is almost 20 meters down. because the toe, you can see the toe is moving as well. Not a lot, but it is still moving. Yeah, in terms of the scale, you can see this is, if that's 4 millimeters, that's the maximum at the formation level. So average is about 2 millimeters is moving. Sometimes that could be still critical for some of the structures that you have within the influence boundary. So again, you can see the classification of the soil and the clay and the moments it. So what we have here is as a sort of mitigation. We talked about the observation. So we measure, we dig, we measure, and then we dig. Now, when we actually come to a situation that, all right, we are getting some early warnings here. The wall is moving more than what we are predicting. So what do you do? Because obviously, once it moves, there is nothing you can do. Yeah, it's irreversible. So, in the observational approach, you must allow for second level of contingency propping. So, if you drop the ground from your current level to this level, you measure it, you predicted something, yeah, you measure it, it's coming within the limits of that you measured, is fine. If it is moving more, you must introduce another level of prop here. So you need to be ready with a contingency propping. What are you going to do? So this is where I think you demonstrate to the third party owners or stakeholders, saying that, look, I'm dropping the ground, but I'm observing, but I have got something in the store that if it moves immediately, I mobilize it. Remember, you have to mobilize it very quickly and all that stuff to put the veiler and put another level of prop here. So this is only one level. So if this had moved more than what we predicted, surely we have to introduce a big veiler here, veiler that goes all around, and then introduce a prop, again similar pattern of props. So that's a contingency propping. And then sometimes we may have to control by additional towers for central prop. For example, for that prop, because that's the longest prop, if this starts to move, we have to think of constructing a tower from bottom up to hold the prop. Obviously, if you decrease the length of the strut by half, your buckling load is 4 times, yeah, L squared. So what happens is, if this is 50 meters, if this started to move, I would have introduced a tower here to hold the prop. So it's like a prop for the tower. So instead of a free length of 50 meters, I'm actually cutting that down to 25 meters. My buckling load in this